Hello. Hello. My name is Parasar. I am a PhD student in physics at IIC. So I'll be taking these tutorial sessions for this statistical mechanics NPTEL course. Uh, so uh, yeah. This is a set of problems I've uh, compiled for the first week. So let's discuss these one by one. Yeah, so the first question, let's look at it. So it says that the density and temperature of a solid of some substance are known, and uh, 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 is this information of density and temperature? Is this sufficient to specify all the variables, state variables of this thermodynamic system? If not, what all can be specified, what cannot be specified? Okay. Yeah, I am on the right link. Okay, that's all right. Let's say the density is rho and the temperature is T. These are given. Uh, so we have uh, only two variables have been specified. Two state variables have been specified. Uh, for a thermodynamic system like solid, let's say, I mean, without any magnetism or any other extra thermodynamic quantities. So we need at least three state variables to fully specify the state of the system. Uh, so indeed, we cannot specify all the state variables of the system with only these two variables specified. But interestingly, what can be specified is pressure in this case. So notice that density and temperature both are intensive quantities. Uh, Materials have this relation. Pressure is a function of density and temperature, or you can write density as a function of pressure and temperature. So if this function is known, so this function depends on the particular substance that we are interested in. It could be different for solids, uh, and also depending on what makes up the substance. This function can change, but in principle, if this function is known, then P the pressure can be obtained, or you can say calculated from the knowledge of density and temperature. So uh, note that we have knowledge of only intensive quantities, density and temperature. We do not have any information of any uh, uh, okay. We do not have any information of any quantity that is extensive. We don't have any extensive quantity like number of particles or volume or energy. So clearly we cannot specify the full state of the system, but like we discussed, the pressure can be known in principle. Uh, but we don't, or let me say, we cannot know any extensive quantity uh, just from the knowledge of pressure and temperature. So the same substance will have the same pressure and temperature uh, uh, as the double the size of the system. We can't know any extensive quantity. Okay, so that's about the first question. Let's move on to the second question. Okay, so in this question, there is a mole of gas which is undergoing two different processes between two states. So the initial state is described by P1 and V1, uh, which are the pressure and the volume of the gas, and the final state by P2, V2. So there are two different processes that the system undergoes between these two states. And the question is, uh, we have to compare the work done by the system. So this is expanding. So let's say that is given. So the gas expands, so its volume increases in both these cases. So the gas does some work uh, on the surroundings. So uh, if you want to compare the work done, we can first note that it is the integral under this curve, under the PV curve, from the initial to the final uh, state, which is nothing but the area under the curve. So clearly, let me try to replicate this again. That didn't work. Okay, so let me just draw a schematic, uh, which is supposed to replicate the same figure in the question. So this is the PV diagram. This is these are P1, P2, and these are V1, V2. So the area under the curve for this process will be this. We draw it a bit more accurately. Yeah, this is the first figure. Uh, replicate it here. So, and the second process is characterized by a straight line, in the PV diagram. So the second one would be it's a straight line joining these 2 points. So clearly, the work done in this second case is more because that curve lies above the above the first curve. So the area under the curve 2 is clearly greater than the area under the first curve. So the work done in that process, the second process is greater. And now coming to the second part of the question, uh, which is about the change in internal energy. It's about comparing the change in internal energy. So internal energy is let me denote this with you. Internal energy is a state variable, which means it only depends uh, on the state of the system and not on the history. So we can say this more accurately as follows. So if you go from one state to another state in different paths, then the change in internal energy depends only on the 2 points, only on the two states, the initial and the final states, not on the path taken to reach the final from the initial. So this does not depend on the path. That is the statement that internal energy is a state variable. Or we can also say that equivalently you can assign okay, just a minute. So you can uh, so u is a function of just the state variables, let's say PV and number of moles. So in this case, we see that uh, both these processes are between the same set of initial and final states. So the path does not matter when you calculate the change in internal energy. So delta U is the same for both. Okay. All right. So now let's move on to the third question. Yeah. So we have nitrogen gas undergoing a couple of processes, and they've been described. So let's get started by trying to depict these processes in, let's say, the PV diagram. Uh, yeah. So the gas starts off at 1 atmospheric pressure and 300 Kelvin. So let's say it is this point. And there is then expanded constant temperature. So this is the isothermal process. This first step is an isothermal process. Uh, so this gas expands until the volume doubles. So if this is V1, uh, the gas expands until this becomes 2V1. That is the first step. And in the second step, it is compressed at constant pressure. So let's say this is P1, the initial pressure, which is 1 atmosphere. So P1 is 1 atmospheric pressure. Uh, and since it's an isothermal process, the pressure finally after this step would be reduced to half because the volume expanded uh, to double the initial volume. So this would become P1 by 2. So uh, and uh, now let's look at the second step. It is now compressed at constant pressure. So the second step is at a constant pressure. So it's what you can call an isobaric process. Uh, so this is the first step. The second step, the volume will have to decrease because it's being compressed. Uh, so it's being compressed until the volume is again the same as the initial volume. So it's now back to its initial volume. So you could draw it like this. So the pressure is constant and the volume has come back to the initial value. So this is the second step. So yeah, these are the two steps that have been uh, uh, two steps that the gas has been subjected to. So now we have to calculate the work done in this process and also the heat absorbed in this process and so on. Yeah, so the idea would be to calculate the work, we would have to do the integral, the PdV integral to calculate the work done. And then uh, uh, we can calculate the change in internal energy uh, because we know it's nitrogen gas. We can roughly treat it as an ideal gas and calculate the change in internal energy. Okay, so let's first do the calculation of work done. So W1 is going to be the work done in the first step. So that's integral uh, PdV from V1 to V2. So this is an isothermal process. Yeah, so this would be yeah. So let me just write these given parameters uh, to start with. I mean to note these things. So the initial temperature is 300 Kelvin, and the number of moles is 2. Yeah, so you can simply calculate the work done in an isothermal process by replacing P with uh, the P from the state equation. So this is going to be nRT uh, integral dV by V from V1 to V2, which is nRT log nRT ln V2 by V1. Yeah, okay. So that is the work done in an isothermal process. So for our purpose, I mean in this particular calculation, so T is T1. It is the initial temperature. So it is 2R T1 log ln2. And now coming to the second step of the process. So now this is an isobaric process. So if we do the same thing here, integral PdV, so that would be so the pressure is a constant in this process. So that would be pressure here, which is P1 by 2. The pressure throughout the second step is half of what we started with. That is P1 by 2 times the change in volume, which is V1 minus 2V1. So this is the change in the volume in the second step. So notice that the gas is being compressed, so the work done by the gas is naturally negative. So this is minus P1 V1 by 2, which is nothing but so we can replace this PV here with the state equation. Uh, uh, I mean, making use of the state equation. So this is nRT. There are 2 moles, so this will be minus R times the temperature here, which is I mean P1 V1 is nRT1, so this is minus RT1, and finally the work done would be the uh, sum of work done in these two processes. Yeah, so that would be 2 ln 2 minus 1 uh, times RT1. So we can plug, T1 is 300 Kelvin, and the value of R if we want to obtain the final numerical answer. So let me try to figure out how to add a new page. Okay, so let me just do this for now. Uh, yeah, where the question is again being repeated, but uh, yeah, hopefully I'll be able to sort this out uh, by next week. So yeah, ignore this, it's the same question being repeated. Yeah, so now continuing from where we left off. So we finished completing the calculation of work done. So now it's the change in internal energy that we have to calculate. Uh, so that we can finally calculate the heat absorbed using the first law. So yeah, okay. So initially, let's see. So in step one, temperature was constant. So it's an isothermal process, and assuming it's an ideal gas, uh, the internal energy doesn't depend on like the internal energy depends only on temperature. So if temperature is a constant, so for an ideal gas, this is the internal energy. So since temperature is a constant in this step, the change in internal energy in this step is zero. Uh, and now coming to the second step, uh, so sorry, was there a question? Yeah, okay. So this is the yeah, this was the change in internal energy in the first step. Now coming to the second step, so the change in internal energy in the second step is 2 times CV times the difference of temperature between the final and the initial states in the second step. Yeah, so uh, let's also quickly try to show the temperatures at various points. So this is T1, this is T1 because this was an isothermal process. Now in the second step, the pressure was a constant, but the volume halved. So the temperature will also reduce to half of its value from the state equation. So if pressure is a constant, the volume will be proportional to temperature. So since the volume has decreased to half of its value in this step, temperature will also do so. Yeah, so the final temperature at the end of all the steps, both the steps is T1 by 2. So this is going to be T1 by 2 minus T1. So which is minus CV times T1. Yeah. So delta U for this for both these steps together is minus CV times T1. So this is nitrogen gas. So at high enough temperature, its CV is going to be 5R by 2. This is molar specific heat capacity because of the 5 degrees of freedom. So nitrogen gas, it's a diatomic molecule. I mean, uh, it's made up of diatomic molecules. And uh, you have 3 translation plus 2 rotational degrees of freedom that will contribute to specific heat. So this is where this 5 by 2 is coming from. Yeah, okay. So that was delta U1, uh, delta U for both the steps combined. And finally, we can make use of the first law of thermodynamics, which is nothing but saying that the total energy is conserved to find the heat absorbed in the process. So the heat absorbed in the process is change in internal energy of the system plus the work done by the system. So yeah, we have calculated both of these. So if you are combining everything, so this is going to be minus 5 by 2 plus 2ln2 minus 1 times RT1, where T1 was 300 Kelvin. Okay, so we just calculated the work done and the change in internal energy and use the first law to find out the heat absorbed in the process. Okay, excuse me. Yeah, now, so moving on to the fourth question, we have what is said to be an isolated rigid container, uh, and it is divided into two chambers of equal volume. So the volume of these parts are, let's say, V and V. Okay, so this chamber has some gas, helium gas at some temperature. So helium at 300 Kelvin, sorry, at 200 Kelvin, and this has neon at 400 Kelvin, and 4 moles of it. This is 2 moles. And now, so this piston or membrane is now pulled. It's removed somehow. It has disappeared, and now the gases can mix, and you have to find the final temperature of the mixture. So first of all, this is an isolated container, so it does not exchange any heat with the surroundings. So of course, these two gases can mix and exchange heat with one another when the partition is removed. But this whole system of these two gases combined, it cannot exchange heat with anything else. Uh, and also it is a rigid container, so the volume of the container stays fixed. So, so there is no expansion or contraction of any of the boundaries. So this first point isolated means that uh, Q total for the full system Q is 0, and rigid implies that they cannot do any work. So the work done by any of the gas, uh, uh, so the work done by any of the gases uh, or the mixture is 0. So the idea is that we have to apply the first law of thermodynamics or the conservation of energy to find out the resulting temperature once the uh, piston is removed. Yeah. So initially the internal internal initially uh, yeah, the uh, initial view of the system is uh, so this is helium, so it is 3 by 2 nRT. So it's a monoatomic gas. So we have 3 here. The CV is 3R by 2, and Similarly, neon is also monoatomic, so this is the initial total energy of the system. So that would be three times R. Okay, let us just leave it like this. I mean, uh, we can substitute for the values at the end. And once the piston is removed, the gases will mix, and you get. Okay, so let me draw some gas molecules here. And so the final temperature is T, and there's a mixture of helium and neon gases. The final temperature is, sorry, the final internal energy is going to be 3 by 2 N1 plus N2 times RT. So both of these gases are going to be at the same temperature T after they reach equilibrium. So yeah, we can simply just equate these two quantities due to the first law, and final temperature is then uh, is this. Yeah, so okay, uh, it's substituting these values now. So that is going to be yeah, which is about okay, which is 800 by 3 Kelvin. Yeah, let me make sure the meet doesn't end. All right. Yeah, uh, so we have another container here, which again has a mixture of gases. Yeah, okay, so it has yeah, so that is the container, and it has N1 moles of gas A whose specific heat ratio is gamma 1. So CP1 by CV1 is gamma 1. The ratio of monospecific heats at constant pressure and constant volume. So this is for A, and similarly for B, these are N2 and gamma 2. Yeah, N2 and gamma 2. So we encountered this like situation, for example, uh, when we breathe the air. I mean, the air is a mixture of various gases. Although most of it uh, is nitrogen and oxygen, both of which are like diatomic and have the same gamma. Anyway, so this is like a scenario that we have uh, uh, like uh, in front of us, or like right around us everywhere. Uh, so we have a mixture of gases with different specific heats. I mean, yeah, different ratio of specific heats. And what would be the the specific heats and the ratio of specific heats for this mixture of gases. So here we in this question we have only two components, but yeah, this can be easily generalized to any number of components and calculated. Yeah, so let's get started with the calculation now. Um, so, uh, uh, so if you want to understand how the specific heats uh, of individual components give rise to the specific heat of a mixture, let's just consider, let's say, a constant volume process. So dV is zero, or uh, yeah, there's no volume change, uh, like at any stage during the process. So this means dV is zero for all the components. So the volume of the mixture is equal to the volume occupied by each of the components. So if the heat, okay, let me write delta Q. If the heat absorbed by the first component is delta Q1, then that would be N1C1 delta T. And the heat absorbed by the second component or the second gas would be N2CV2 delta T dt. Of course, dt is same for both of these gases because we have a mixture of gases and yeah, they are in uh, thermal content. I mean, it's a mixture of these two gases, so the temperature is same for both. Now, the heat absorbed by the full system would be the sum of these two, which we can write as N1 plus N2 times some CV effective heat capacity, which we want to calculate times delta T. So this has to be the sum of the above two quantities. So then we see that so you have to take weighted specific heat capacities with the amount of substance or the number of moles here. Take that sum and divide that with the total number of moles. So that would be the CV of the of the mixture of gases. And similarly, uh, CP also takes a similar form. So if the pressure of a mixture of gases is constant, uh, we have to, yeah, sorry. So the CP is the specific heat at constant pressure. So the full mixture is at a constant pressure, then the individual components pressure would also be constant. So the partial pressures of each of the components is also constant. So if dP is 0, let me just write that. This is when we define CP. Yeah, so then dP1 is 0 and so is dP2. Yeah, so we will get a similar uh, expression for the specific heat at constant volume. Yeah, so we have both these quantities and all it remains is to take the ratio of these two quantities. Yeah, again, so this problem will appear. So Uh, please contend with this for now, but I'll try to get rid of this or fix this. Uh, yeah, so now gamma is Cp by Cv. So we can in fact try to express this in terms of gammas, gamma 1 and gamma 2. Um, let's just go back here. Gamma is Cp by Cv, okay, and for an ideal gas, Cp minus Cv is R. So this is true for a single gas. I mean, with a so this relation would be true for each of the individual gases, individual components, and also for the mixture. So the mixture also is an ideal gas. Um, so we can express Cv. So gamma minus 1 would be R by Cv, or Cv is R by gamma minus 1, and Cp would be then gamma by gamma minus 1. So we can substitute these for individual specific heats here. So the final gamma is Cp by Cv, which is from these two set of boxed equations. It's going to be N1 Cp1 plus N2 Cp2 by N1 Cv1 plus N2 Cv2, which is okay. Yeah, so finally we managed to express the ratio of specific heats in terms of the given quantities. All right. I'm sorry, just give me a minute. Yeah, sorry about that. Yeah, so I've also included a couple of questions on heat engines, since it is there in the week 1 syllabus. Yeah, so it's a reversible heat engine operating between two temperatures. The efficiency is this. So which is 25%. Okay. And yeah, so we have a heat engine. This time it's not reversible. Uh, I mean, it could be any heat engine with this given efficiency. So this efficiency is 5%, and in every cycle, uh, the work it does is 10 joules. Um, yeah, so this is an each cycle, and we have to find the total heat extracted from the hot reservoir in 100 cycles. Yeah, so any heat engine, if you think of it schematically, it's going to extract heat uh, yeah, it's going to extract heat uh, from a reservoir, and so let's call this Q hot, QH, or this is a heat extracted from the hot reservoir. Uh, so its purpose is to do some work. It's an engine. It does some work by by leaving some heat to some reservoir at a lower temperature. Sorry, this QC. So the second law of thermodynamics puts theoretical limits on how much it can uh, extract. I mean, how much work it can extract per the heat extracted or the heat taken from the hot reservoir, right? That is the efficiency, which is this ratio of um work done by the engine and the heat extracted from the hot reservoir. So this is 5% or 1/20. Yeah. So in each cycle, it is going to extract 20 times the work it does. So which is 200 joules. And uh, the question is about uh, the total heat extracted in 100 cycles. So this is per cycle. So in 100 cycles, uh, heat extracted is yeah, it's going to be 20,000 joules, or it's 2 into 10 to the 4 joules. Okay, all right. This one is about calculating the change in entropy, calculating entropy changes for an ideal gas in various processes. Yeah, so here's how we can calculate the entropy change for an ideal gas in any process. So we know uh, this is the first, excuse me, this is the first law. Sorry. Yeah, so to calculate the change in entropy, we only need the initial and final states. So again, entropy is also a state variable. So entropy is a state variable. So we need not know the path taken between the two state, the path taken between the two states to be able to calculate the change in entropy. So notice that in the question, nothing about the process being reversible or not is given because it's not required. So whether the process is reversible or irreversible, the change in entropy can be calculated, uh, making use of this equation. Uh, so let me say uh, between the same set of states, let's say some A and B. So if A and B are two states, then whatever path you take, it could be like reversible or irreversible, like I said. The change in entropy would be the same. Uh, so the second law says that there's a quantity called entropy, which is a state variable. Okay, anyway, so now we can uh, just make use of this equation. Uh, Make use of the first law in this written in this form. Uh, so this equation is general. I mean, it is true for any gas, any substance. So now we can make use of the fact that we are uh, uh, that uh, that we are dealing with an ideal gas. So U would be NCVT, and this is uh, the equation of state. Yeah. So if my U's and V's are looking the same, yeah. So this is where we have used the fact that this is an ideal gas. Yeah. So we now know the particular functional forms of internal energy and the pressure from the state equation. So you can simply plug those there. So if we want delta S, that would be integral of this expression. It's NCB ln T2 by T1 plus NR ln B2 by B1. Yeah, so this is true for any process. Uh, okay. Yeah, I think. Oh, now the questions are gone, I think. Yeah. Anyway, so uh, yeah, so we have derived the change in entropy for an ideal gas for any process or between any two states. This is the change in entropy. This is the difference in entropy. So now we can apply this to these two cases simply uh, to solve these questions. Uh, so the first one is it's a monatomic ideal gas expanding at constant temperature. Uh, so it's monoatomic. So that means CV is 3R by 2 and it is given that N is 1. So it expands at constant temperature to double the volume. So T1 is T2 and V2 is 2V1. So delta S would be RLN2. And now the second one, the second question. In this case, we have diatomic gas, again 1 mole. So that means that CV is going to be 5R by 2. And okay, it's here. Constant volume from it's heated at constant volume from 200 to 400 Kelvin. So if you substitute these here, delta S is going to be uh, 5R by 2 ln 2. Yeah, so this is the change in entropy of an ideal gas. Yeah, so the main simplification comes from, of course, the fact that this is an ideal gas, and we can make use of these two relations, this and this. Uh, Once we have these, and we can then use them in the first law to get to get an expression for the change in entropy. Yeah, so similarly, can this expression can be used to calculate the change in entropy between any two processes. Yeah, so finally, I have included also a question on probability distributions, since there are some questions, practice questions on this, on probability distributions. Yeah, so it'll also be useful to do these integrals. I mean, it's a good exercise uh, to do integrals of the form we will see here. Uh, yeah, anyway, so let's get to this. So it's a continuous probability distribution with support only on the positive real numbers. So first of all, since it's a probability distribution, A has to be positive, and uh, and for normalization to work, for the probability to be finite, we need B to be positive, of course. Uh, for this integral to converge. Yeah, anyway, we have to find the normalization constant A, and we need this integral. So since it is 0 anyway for x less than 0, we can do this from 0 to infinity. So this has to be 1. Yeah, this is actually a simple integral. Uh, so this is just a derivative of this. Uh, this has to be 1. So finally, uh, yeah, so we see that A minus A by 2B times minus 1 is 1. So A is 2B. So this is the normalization constant. Yeah, that's right. Yeah. So this is the normalization constant A. And we then have to find the mean of this probability distribution. Let me make sure the meeting doesn't end. Yeah. So the mean is simply integral. So in this case, it is simply all right. So we have to do this integral now. So A we know is 2b. So so there is a very nice and cool trick to do integrals of this kind. So here we have x square e to the minus bx square. So first of all, we start with uh, the Gaussian integral 0 to infinity dx e to the minus bx square. So this is going to be, I think, so from minus infinity to infinity, I think it is square root pi over b. Yeah. So from 0 to infinity, it would be half of that. And now the cool trick is to take a derivative under this integral sign. This is called the Feynman's trick. We take derivative with respect to this parameter b. Okay. Let me write it more legibly. Yeah, so this is very standard and very often used trick. Uh, uh, so on the right hand side, it's simple enough to take this derivative. So it's going to be this, and uh, this derivative with respect to b brings down whatever we want into the integrand. So so this is going to be so this is going to bring down minus x square. Actually, let me check if the Gaussian integral I wrote is correct, including the factors. Um, yeah, it is correct. Yeah, that's fine. Yes. Yeah. Okay. Uh, Great. So we have this now, and so finally, what we see is that this integral that we want nicely comes about. So finally, it is square root pi by 4b to the 3 by 2. All right. Okay. So uh, and what we wanted was 2b times this. So expectation value of x is, yeah, or it is, let's say, square root pi by 4b. Yeah, so we can also, we have calculated the mean now. Let's say to illustrate this further, let's also try to calculate the expectation value of x square. Again, yeah, sorry about this. Let me just try to strike this out. Yeah, so now expectation value of x square is uh, yes, so we have ax e to the minus bx square. It's going to be x cube e to the minus bx square. All right, so now so we did this integral x e to the minus bx square when we were calculating the normalization. That was simple enough. Uh, but now we want x cube multiplied by the exponential. So you can see that we can take this as a starting point and use the trick to bring down another factor of x square. So we will finally get x cube times the exponential in the integrand, which is what we want for this calculation. Okay, let's quickly try to see that. Try to do that, complete that. So we have this. Yeah, so this integral is 1 by a, which is nothing but 1 by 2b. Let me write this as a starting point. Integral 0 to infinity dx x is one. This is 1 by 2b. Yeah, and now we can use the same trick here. You can apply this operation of taking the derivative with respect to b. And let's see. So that would bring down minus x square again. So integral 0 to infinity uh, with a minus sign x cube e to the minus bx square. This thing is going to be uh, minus 1 over 2b square. All right. So, okay, let me just remove this. So what we want is expectation value of x square. So expectation value of x square is uh, a times this integral. So it is 2b times so by 2b square, which is 1 over b. Yeah, let me try to write it. Yeah, okay. Yes, uh, so to summarize, we've used the Feynman's trick of taking differential under the integral sign to calculate these integrals. Yeah, so these type of integrals also show up when calculating various quantities using Maxwell's distribution. And I mean, these sort of tricks can be used to calculate integrals like this. You can also, I think, do some get a recursive relation. Uh, 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 like what I mean is some relation which relates uh, integrals. This is in. Some relation which relates in plus 1 to in and so on. Uh, so yeah, I mean, these sort of integrals can be obtained like this. Yeah. Okay, so that's all. That is all the questions I have for today. Okay, all right. So let me uh, let me conclude by saying that uh, you can give feedback about the type of questions discussed. Uh, if you watch this video, if you watch the recorded version of this video later, you can give me feedback about the type of questions being discussed, uh, or uh, any changes that you may want to see in the type of questions that are being discussed. So I've formulated these questions based on the content in the NPTEL platform and the questions in the assignments. Uh, yeah, so if you have more ideas or suggestions, please let me know. Uh, please let me know by email. Okay, so yeah, so let me end it here. Let me stop the recording and and end the meeting.